synchrotron emission to study the magnetic field of the Milky Way. There's a worldwide collaboration called the Galactic Magneto-Ionic Medium Survey, which is mapping the sky at a range of frequencies to determine the structure of the magnetic field. John proposes to review that program and also talk about some of the findings that have come out of that. So, would you please welcome Professor John Dickey.
Thanks very much, Steve. And let me start off by saying thanks to Stefan for showing the video of the Falcon Heavy launch and for pointing out Australia in the background. We saw Australia in the background thanks to my colleague Simon Ellingson, who had time. Usually, spacecraft rise in the west, go over and set in the east in about 10 minutes. This one, after the launch, about 40 minutes later, came over from west to east, drifted over towards New Zealand, and then came back, and then stayed over Mt.Pleasant for about 2 hours after that. And so all of that video came through our radio dish, and I don't think any other dish could have seen it for that entire time. So yeah, we were happy to help out. Let me say also up at Bisty Tier, where our new optical observatory is, we now also have a new dome which has about an 8-meter radio dish inside. They tracked the launch on Sunday evening after that. So we worked hard, they worked hard, and we're happy with that too.
So they built an 8-meter dish in a few days.
Yeah, I'm not sure if it's 8 meters. It was about 6 meters, I think. I'm trying to remember. But yeah, the dish itself came in 2 halves, which were about the size of that section of wall there, a little bit bigger because they were half circles. And but the 2 halves fit into a shipping container. And then they put it on top of a 20-foot tower as well. You can see it from the Midlands Highway, but it looks like our observatory dome. And because of where the trees are, you can't see both of them together, at least not that I've seen. So hopefully nobody will notice it. But,
And it's there for keeps.
well, and we've got a 10-year contract with them, but yeah, and they would take it away probably if we required them to. But I think it's safe.
Is Elon going to open it?
Well, we would love, I shouldn't even be here telling you. We would love to do a press release from the university, but they don't want a word of this to get out. It's not that it's a military secret or anything, it's just they don't like people tracking what they're doing on the ground. They love to put up videos on the web and do their own public relations, but they don't want the university doing public relations for them, unfortunately. And let's see, let me say also, I read Steve's President's report from last month, and I do want to say thanks to everybody for the work that you've done at Mt.Pleasant. You're turning Mt.Pleasant from a radio observatory into a radio and optical observatory, and we're very proud of that. We're very proud of what you've done. And if I can, I'll come around April 23rd, you said?
Yes.
21st, yeah. But anyway, you've made a lot of improvements to the shipping containers, and I'm very happy. Yeah, so this is a talk that I gave up at Astronomical a few weeks ago, and it's a little on the technical side, but I'll try to zip through the heavy mathematics and mostly just show you pictures of the sky. But they're pictures of the sky that pretty much nobody has seen before. So you can just kick back and stare at them and see if they make any sense to you. But they don't make a whole lot of sense to anybody. But what I'm going to do is, if you can just turn down the lights, I'll talk about steps to the polarization horizon. And if I can just kind of give you an idea of what the polarization horizon is, I'll be happy. Let me run through a few of these names. This is the Galactic Magneto-Ionic Medium Survey, because several of them are Tasmanians. The leader is Tom Landecker, who was for 20+ years the director of the Dominion Radio Astronomy Observatory in Canada. That's the Canadian equivalent of the U.S. National Radio Astronomy Observatory, or our CSIRO, Astronomy and Space Science. He's actually an Australian, not from Tasmania. He's from Sydney, and did his first radio astronomy work in the early 60s at Sydney University. But his sister lived here in South Hobart for a long, long time, and so he used to come and visit us quite a bit. Mike Bolovan is a South African, now living in Canada. Ettore Caretti is Italian, He spent many, many years at Parkes Observatory, but now he's director of the Italian Radio Observatory in Sardinia. Kevin Douglas is Canadian. Zhao Sun is Chinese. He's a professor at the University of Yunnan, but he also spent quite a bit of time in Australia, about close to 10 years, I think, at Sydney. Brian Gensler is an Australian. He was actually Young Australian of the Year some years ago, but now he's director of the Dunlop Institute at the University of Toronto. So it's a very international collaboration. We have people from China, people from Germany, people from America and Canada, but it's fairly heavy on the Australians. Dave McConnell is a Tasmanian. He's now the director of the Australian Square Kilometre Array Pathfinder Telescope, and based in Canberra. And let's see, there's a couple of other Tasmanians. Alec Thompson is a PhD student now at ANU, but he did his undergraduate and honors degrees here at UTAS. So anyway, it's a big group, and this is what we're doing. Now, you know there's cosmic rays in the galaxy, and cosmic rays are electrons and protons, and some heavy element nuclei as well. But what makes them rays is that they're going almost at the speed of light. And the particles, the cosmic rays, particularly the electrons going at the speed of light, are tied to the magnetic fields of the galaxy. Milky Way has magnetic fields. They're weak. They're not as strong as the Earth's magnetic field, but they're actually, within about a factor of 1,000 as strong as the Earth's magnetic field, a few hundred to 1,000. And the magnetic fields hold the cosmic rays in the galaxy. If it weren't for the magnetic field, the cosmic rays would all just spill out at the speed of light and fly away. And that could happen, but it doesn't happen because the cosmic rays are tied to the magnetic field. The magnetic field, well, some places may go out, goes in different directions, but much of it circles around the disk of the Milky Way, kind of the way spiral arms circle around in the disk of a spiral galaxy. Now, that we think we understand, but we don't have a good picture of it. You can't really get a good picture of it from the Earth because we're right in the middle of it. So the challenge that the GMIMS consortium has taken on is to try to map the Milky Way's magnetic field and the cosmic rays, and in addition, the ionized gas, that is, electrons and protons that are free, not going at the speed of light or anything, just freely floating between the stars. All those things come together to make what we call Faraday rotation. And the Faraday rotation is described in this picture. Here is the synchrotron emission. Synchrotron emission simply means cosmic rays spiraling around magnetic fields. And here the B letter means, magnetic field. But then the polarized emission comes from there to us, propagating or traveling through clouds. It's all right.
Keep going.
Yeah, that's right. I think that was just the power there.
Yes.
There we go. Through the clouds of stuff between the stars. And that rotates the polarization vector. Polarized, particularly linearly polarized light, has a vector which is the direction of the polarization. And we call that Stokes Q and Stokes U. And those are actually orthogonal vectors which describe the polarization, so-called Stokes parameters. And we work a lot with those Stokes Q and Stokes U, or the square root of the sum of the squares, which we call the polarized intensity. And this survey is not the very first to study polarized intensity, but I think it's by far the best that in radio frequency survey of the Milky Way that we've ever made. And we made it with two telescopes. The one on the left is in Canada, in British Columbia, a place called the Dominion Radio Astrophysical Observatory. And the one on the right is Parkes. And this whole thing began with Professor Lendiker, who was for a long time the director at DRAO. That telescope is the same size as ours at Mt.Pleasant. It's 26 meters. And it was built even earlier. Both of these two telescopes were built in the very early 1960s. But they're both still in operation. And if we hadn't had them, we wouldn't have been able to do this survey. So it's not just about the telescope, it's more about the receivers. when Tom decided that we should do the survey, the first thing he did was sit down and design the radio receiver that could do it. And this is a polarization sensitive receiver operating from a frequency range from 300 to 900 megahertz. In that frequency range, the biggest problem is human-generated radio interference. Everything from mobile phones to, they had problems with microwaves at parks, they had problems, people have had problems with electric fences, all kinds of things can generate interference. And we have had to black out more than half of that frequency range from 300 to 900 megahertz because it's simply polluted by human interference. But there are gaps in between the frequencies where people are generating stuff, and they're not always open, but when they are open, we can use them. And so we've been fortunate about that. Here's the receiver on its way. It looks like it's going down, but actually it's going up to the focal cabin. Because interference is even generated by the other receivers in the focal cabin. We had to go up. You can sort of see there's a ladder up one of the feed support legs. Every night after sunset and every morning before sunrise, we had to go climb up and turn off all the other receivers in the focal cabin so that they wouldn't interfere with ours. But of course, during the day we couldn't work, so they wanted to all turn back on, so we had to go back up and turn them on. And that, you kind of get used to it, although the one thing that let me step back here. One thing that I didn't know about parks is when it's pointing straight up, which is the stow position when you go up the ladder, and the wind is blowing, you don't really notice it while you're in the shelter of the dish. But once you get up to about this point here, suddenly you're above the lip of the dish, and the wind just about picks you up and throws you off like a, like a free balloon that some kid is let go. It doesn't throw you off because you have a climbing harness on and you're linked to the stairway with a powerful piece of wire. But if it weren't for that, it would be very dangerous. Anyway, so this is what we call Stokes' eye, which means the total intensity of the radio radiation from the sky. And I'll keep bouncing back and forth between the two telescopes and the two surveys. The Canadian survey covers the northern hemisphere and down to about -20 degrees declination. The Parkes telescope covers the southern hemisphere and up to about +30 degrees declination. So we have about a 50-degree strip covered by both surveys. And in this case, it's the PRAO, so the Canadian survey. And you see this big white kind of shape. These coordinates are now galactic latitude and galactic longitude, which means the galactic plane goes right across the middle. And this big thing here is sometimes called the North Polar Spur. It's been known since the 50s. In fact, it was observed, I guess, by Draper very early on. And it's a very bright thing that we think is fairly close by, that goes up from the galactic plane and arches over the northern hemisphere, the North Galactic Pole, and back around. The North Galactic Pole is at the top, the South Galactic Pole is at the bottom. The North Celestial Pole is this little dot right here. And the South Celestial Pole is right in the middle of this. So we just converted the coordinates, and this is, of course, a Cartesian projection, so it's a bit like a rectangular map of the Earth. The bottom bit is stretched out like Antarctica is on Earth maps. Now, this is what we call moment zero of the polarized sky. The polarized sky, you see some things that are very similar. For example, the North Polar Spur is even brighter here than it was before. Let me step back. This is the unpolarized light, and this is the polarized light. Notice how the galactic plane just about disappears. The galactic plane is so bright in the unpolarized light, and that's because we can see all the way through the galaxy in unpolarized radiation. Nothing absorbs it, and so we see it all. So naturally, because we're in the middle of the disk of the galaxy, and the galaxy is very, very big, as we look across the disk, things just get brighter and brighter. The center of the galaxy is right about here at 0 longitude, and that's the brightest point of all. in the unpolarized, that is the Stokes eye emission. On the other hand, it's not particularly bright in the polarized emission at all. What we mostly see is the high latitude stuff. With the exception of this over here, this is called the fan region, and it was discovered back in the 50s when people first started looking at polarization. It's supposed to look like a fan, but I don't know if it looks like that to me. It looks more like a crab to me. But anyway, it's an interesting bright region. Nobody knows where it is. It might be as far as 3 or 4 kiloparsecs away, that is in the Perseus arm, or it could be very close. I've listened to people argue back and forth, and I'm not going to jump to conclusions. But if we knew where is the polarization horizon, then we would know how far we can see in the polarized emission. And we don't know that yet. And that's what I'm trying to figure out, what we're working on in this survey. Now here in the south, this is the Stokes eye from Parkes. Now we fill in the gap that we didn't see before, but on the other hand, then we all see the northern sky. So there's another big white cutout, which is everything to the north of where the Parkes horizon is. Again, now we can see the galactic center very well. The galactic center goes directly over our heads, but it's a little bit to the south, as seen from Parkes. But still, we've got a good view of it. There's several other things. This is, I guess, Virgo A. This is Centaurus A. This is the LMC. There's several things, but mainly the Stokes eye is dominated in both hemispheres by the Milky Way galactic plane. But here also, you do see the plane, but it doesn't dominate the polarization. Polarization, well, you see a few things. This actually is probably part of the North Polar Spur. People argue about what some of these other things are. A few of them actually correspond to things that we kind of know about, like fairly nearby, the Orion Nebula, for example. You can find in polarization. It's not the brightest thing, but you can sort of find it. It's over in here somewhere.
Is it the same frequency as the northern one?
You want to see the northern one back again?
No, is it the same frequency? 15,
No, it's not. And in fact, let me show you this. This shows the frequency range for the Parkes survey, 300 to 480 megahertz is what we're working with. But in the DRAO survey, it's 1270 to 1750. So although the Parkes dish is 64 meters, and the Dominion dish is only 26 meters, they have actually much higher resolution. I don't know if you noticed, but the southern survey looked blurrier than the northern survey. That's because even with the bigger dish, the wavelengths are so much longer in the low frequencies that the beam or the resolution, the beam is larger and the resolution is also coarser. Good question. More questions, by the way. I don't want to just talk on and on here. I'm happy to just answer questions even if I don't finish my talk. So
it might be a silly question, but why don't we then use the higher frequencies?
That's not a silly question at all. People did that for 50 years.
Okay.
And it wasn't until about 10 years ago that people appreciated you can't get away with that. You have to go down to the low frequencies to really study the polarization. And, you know, it made a lot of people feel a little silly, I think. But that was part of the reason why I got into this field, because it makes it a lot more interesting. And just to answer your question in a word, at the high frequencies, although you have a better resolution on the sky, you have much worse resolution in what we call rotation measure. And I'll talk a little bit about rotation measure, but that in the end is the whole game, is to resolve in rotation measure the polarized emission that's coming to us from the galaxy. And let me work along that theme as I go along, but that's the fundamental question. Yeah.
Another question I have is, between the two observatories, why aren't the ranges meeting as opposed to having such a large gap between the two stations?
Well, let me say this. There is an overlap between the two surveys, but because the frequencies are different, you wouldn't have noticed it. Let me bounce back and forth. I tried to get these adjusted to the same scale. So if we go from here to here, there's actually a lot of overlap. For example, at longitude 0, is close to the edge, close to the southern horizon from Canada. And if I now step down to here, well, longitude 0 is well within the horizon for New South Wales, for Parkes. But this looks pretty much identical to what we saw before. This is the unpolarized. And the two surveys are highly consistent in the unpolarized radiation. But if you look at the polarized radiation, and that's this versus that, they're not that consistent at all. In fact, if you plot a plot of the brightness of one and the brightness of the other, they're completely uncorrelated. And that's a tip-off that the polarization horizons are different in the two surveys. And in the lower frequency survey, the one for Parkes, we're seeing just quite a small volume around the solar neighborhood. But in the higher frequencies, we're seeing a much larger area. Still not the whole galaxy, but a larger area. Question? Questions? Okay, well, let's move on. So here's the table. The answer to the question about the rotation measures all has to do with these funny numbers here. And nobody really appreciated that. Well, you know, it's funny, there was a British astrophysicist in the early 60s who wrote a paper about polarization and how it propagates that explained really everything, but it wasn't picked up. It just wasn't understood. People read it, and it was cited, but people didn't think through what the guy was saying. And it wasn't until about 2005, 2006 that a couple of guys in the Netherlands, Brentjens and De Bruyne, wrote a very important paper that explained how you really should do these surveys. And it was on the strength of that the GMIMS consortium was built. And so I said I showed this at Astronomical, and I'm not going to hammer in the mathematics. In fact, I'm going to skip over most of the mathematics. But this is a very important equation. This is the one which was in the paper from 1966 by Byrne, but people didn't really get what it was saying. And what this equation says is that there is a Fourier transform relationship between the polarization as a function of wavelength squared and a spectrum. And it's not a spectrum versus wavelength or a spectrum versus frequency, as most spectroscopists like me usually work with. It's a spectrum versus what's called rotation measure. And the little Greek phi here means rotation measure. And part of the reason I got interested in this is I spent most of my career looking at spectra, radio frequency spectra from spectral lines, like the 21 centimeter line. And here's a whole new kind of spectrum that can be computed through an equation like this. And so I'll pass on from the equation and show you some of such spectra. This is a spectrum with a pair of spectra, one from the DRAO survey, one from the Parkes survey, looking in the direction of a pulsar. And I chose a pulsar to pull these out because we know the rotation measure of the pulsar, and we know the rotation measure all the way through the galaxy in that direction. The rotation measure is simply a measure of how much the plane of polarization has rotated as it comes from the source of the radiation to us. And to understand how that corresponds to actual distance along the line of sight is the whole point of the survey. We want to understand how the rotation of the plane of polarization, so-called Faraday rotation, maps out into a three-dimensional picture of the Milky Way. And so these spectra, and notice that if you can read the numbers, in the DRAO survey, the Canadian survey, these numbers go 0, 100, 200, 300, minus 100, minus 200. And the emission that we see from the galaxy in the polarized light is all concentrated in about plus or minus 40 or 50 in these units, which are radians per meter squared. In the low frequency survey that we did with Parkes, the whole range is from minus 30 to 30. That is, it all fits inside this big bump. But now we can resolve in the spectrum a whole lot of separate bumps, which are all blended together in that one big bump in the center. The challenge of a polarization survey is to resolve the emission into different rotation measure peaks. In the same way that when we look at a spectral line, we have several galaxies far away. Each one has its own bump, which corresponds to its own redshift in wavelength or its own frequency because of the Doppler shift. Here it's not the Doppler shift, it's the rotation of the plane of polarization. And here's a few more. We have thousands and thousands of these, thousands and thousands, and I won't bore you with too many of them. This is another image of the sky, but made not using the synchrotron emission, made using faraway extragalactic radio sources whose polarization is also rotated by the Faraday rotation, by the magnetic field of the Milky Way. And this actually corresponds pretty closely with what we see in the DRAO survey. Here is just averaging over all the sky that's seen by each survey. And the green and blue are the northern hemisphere and the southern hemisphere of the Milky Way, as seen in the Canadian DRAO survey. This is plotting against rotation measure. The red and the black, which you see are actually quite different, are the northern hemisphere and the southern hemisphere looking at the Park survey. And the spread in rotation measure is much less in the Park survey, but probably it's actually consistent with what's seen in the Canadian survey. It's just the Canadian survey blurs it all out. And every survey of the Milky Way in polarization before this blurred it all out in the same way. And that was the breakthrough that people had 50 years after the fact in terms of understanding how to do radio polarization surveys. And yeah, these are sort of details on how the polarization horizon comes about. Why is it that we can only see a certain distance? I won't drag you through all the theory of that. But what I want to do is just show you a few more maps, computed in different ways, of the polarization. And then, if you want, I can show you some statistical analysis that I've done to try to understand that. This is the total polarized brightness. This is what we call moment one, which shows the average rotation measure in different places, working our way up and down through the spectrum.
Excuse me.
Yes.
Most rotation is in the red, is it? How do I read that scale?
Yes, so you read the scale positive and negative. Negative means that the rotation has been anti-clockwise, and positive means that the rotation has been clockwise. Or what that means is, if we have a positive rotation measure, the magnetic field is pointing towards us. And if we have a negative rotation measure, the magnetic field is pointing away from us. Just as the magnetic field in the northern hemisphere points out from the Earth and then back into the Earth. Well, the Milky Way's magnetic field isn't that simple. You don't see all red on one side or black on the other. In fact, it's quite complicated. But you do see some pretty big regions, and this is again the North Polar Spur, that's all pretty gray and black. And that means that the magnetic field is very coherent there. It's pointing the same direction over that whole area of the sky. We see that a little bit down here in the south as well. But notice how going close to the galactic plane, there's a lot of jumble between red and black.
And how does that relate?
Sorry?
How does that relate to the BZ, which is what Aurora hunters are interested in? They want to know when the BZ is negative. You're talking about the BT, is that right?
The VZ or the
BT? You had BT on the map.
On the coil.
On the first slide, you
yeah.
had BT.
Well, people argue in the Milky Way about BZ, which to us, and I'm not sure if this is what you're referring to, but to us, we live in the disk of the galaxy, like the top of this table. We live inside there. And the question is there a coherent magnetic field pointing in either the positive or negative direction perpendicular to the plane? That's what we call BZ. Now the auroral people on the Earth, they worry about the field direction as it as it guides the solar wind particles into the ionosphere. And when there's a solar flare or when there's solar activity, you get a strong aurora, depending on the BZ, that is the component of the magnetic field on the Earth, pointing vertically. Is that what you mean?
Yeah, that's right. So if I look for a VZ of a negative VZ, and then they know there may be an aurora. You have to have a negative VZ to get an aurora. A strong aurora. Yeah.
And I know what you're talking about, but I don't know. I mean, that's not what I'm talking about here,
Right.
because I'm talking about a much larger scale.
Yeah.
I don't know if there's an analog to the VZ, which I think is a magnetospheric thing. I think that has to do with the brisk magneto tail and how the particles from the solar wind get into it in order to then come down to the auroral oval.
Right.
And, you know, people talk about galaxies having tails, magnetic field tails. People talk about leakage of particles out of galaxies, like cosmic rays, out of galaxies. But we don't know for the Milky Way, we don't know it in that much detail yet, I think is the thing to say. People who've been studying the aurora, they can fly satellites out there. You know, they can do all kinds of detailed studies that we can't do yet in the Milky Way.
I've got a question. We just go back a bit.
Yeah.
When you were talking about the different frequency ranges
Yeah.
between Canada and here,
Yeah.
and that what's happening down here is better for what you're trying to determine.
Well, it's not quite that simple, but it's fundamental, let's put it that way. It's good.
Why hasn't Canada gone to the same frequency range?
Well, yeah, they want to. And the goal of the GMIMS consortium is to use telescopes all over the world to do both hemispheres of the sky over the full frequency range. So far, we have these two surveys that have been well completed. There's another one with parts at an even higher frequency that's being analyzed. That was taken by a Dutch woman, and she's actually working with a Chinese guy to try to finish that one. There isn't really a telescope in Canada that could do what parts did. Their biggest now radio telescope is that 26 meter that I showed a picture of. There is one in America, the Great Bank Telescope, but it doesn't have a low frequency system on it. Could, but you know, you have to spend some money and get the telescope time. There's a telescope in Effelsberg in Germany, a 100 meter telescope, which could do a pretty good job of this. And they have a group, part of the GMIMS group, who would probably want to do it. They don't have the resources to do it yet. I know that they would do it if they had the telescope time and the money. And it's not really that expensive, but the telescope time on that telescope is very expensive. So we're working our way there. The thing is, at those low frequencies, you really need a big dish. Otherwise, you have,
I think the reason it's tight because of this side.
yeah, because the resolution on the sky is lambda over d.
Thank you.
So could you, I suppose it would be too expensive, look at using a non-terrestrial way of gathering your data? So something that's already space station or satellites that are out of the Earth's atmosphere, so you get better data coming through?
Well, people told us that, you know, you don't need this telescope time because you can just find the data in archives or in other ways.
Mm-hmm.
But it's not really out there. You have to take it again. And it took us, it took us 5 years. We didn't have the telescope at Parkes for 5 years. We had the telescope for about a month, a year. And you know, I was up there for 3 or 4 years. And for a week, you know, my share was a week, and other people came in to do the other weeks. Yeah, the data isn't really, it doesn't really exist. People claim that this stuff had been done before and we didn't have to do it again. But if you then start working with the data, you find it's not nearly that good.
So you couldn't gather new data in that way, non-terrestrial?
Well, you know, people talk about putting a radio telescope in space, but there isn't any. Well, the Japanese and the Russians have put what's called very long baseline interferometer radio telescopes in space, but they couldn't do this, they're much smaller. Someday we'll have a big dish, like a Parkes type dish in space, but that's probably a century or less. Optical telescopes go into space a lot because you have to get above the atmosphere. But for this kind of work, the atmosphere isn't too much of a problem. It's a little bit.
What about the other way around, John, the higher frequencies in the southern hemisphere?
Well, that is the one that's still being processed. That's a Parkes survey at about 1600 megahertz. About the same as this one. This one was 1270 to 1750, and that's about the same. And so that data was taken, 6-7 years ago. And then it kind of sat in the can for a while because the Dutch woman who took the data and is in charge of that part of the project applied for funding to fund a PhD student who could have done that. But she didn't get it. Now she got a grant. It's a Netherlands-China grant, and so they can hire a couple of Chinese PhD students to reduce the data. Just getting this stuff processed is a 3 to 5 year job. It's amazing how much calibration and checking and testing you have to do. And although it looked like a big list of names, it's still kind of an arcane field, and not too many people are working on it. It's not like extragalactic astronomy or cosmology or something. So we're manpower limited, let's put it that way.
But the data's there.
That bit of the data is there. Yeah, that bit of the data is there.
Is it something you could use a citizen science project?
You know, I thought about that, and before I came, I should say, I had another project that I'm working on that really could use some citizen science help. And maybe next time, if you guys invite me back, I'll work that one up. I tried to work it out, but I had this one that I just presented, and I figured I'd tell you about this, even though it's pretty technical. But yeah, a lot of things could be citizen science projects. This one, it'd be a bit of work to get it into that form.
Just observation at this point, but 300 to 480 megahertz seems to generate a lot of detail. Why not a lower frequency? Why not a higher low frequency? What caused you to determine that 300 to 480 megahertz was an optimal area to observe?
Yeah, I think it probably was, but that's a tough question. The reason we observed at that frequency was we hoped to observe from 300 all the way to 1,000 megahertz. And so that receiver that I showed you with the kind of Christmas tree, that actually could do, and we did collect the data from 300 to 1,000 megahertz. And there was a gap around 500 where there's a bunch of TV stations where it's just never possible to observe. But it turned out that the interference was so bad at the higher frequencies that we couldn't use that. And there again, it took 2 or 3 years of trying before the guy, Mike, who was in charge of that part of the project, finally said that we're never going to be able to get this.
Was that also the result why you decided on 300 as your
As a
base?
lower limit.
Because the lower frequencies were also
If we had known that we couldn't use anything above 500, we probably would have tried to do 150 to 450 or something like that. What's happening as you go to the lower frequencies, the wavelengths get longer and longer. So 300 megahertz is 1 meter wavelength. And that means that the thing you put at the focus of the dish is going to be several meters across. And we didn't quite go there, but yeah, we went down actually a little bit below to 300 megahertz. But to go to, let's say, 200 megahertz, then you're talking about 1.5 meters, and things get pretty big. You could do it, and I think it would be worth doing it. But 300 is sort of a good place to start. The ionosphere gets worse and worse as you go down in that area. So, you know, you need more correction for the ionosphere. You still have to correct for the ionosphere here too, but it gets worse and worse. So, yeah, that's kind of a debatable thing. But, yeah, the data we got is pretty good.
So something outside of Earth's atmosphere would actually be really beneficial.
Oh, it would be fabulous. It would be fabulous. If you could get outside the Earth's atmosphere, well, I was on a NASA committee a couple of years ago looking at Explorer class missions. And one of them was to look at, from the Big Bang, when the 21 centimeter line first goes into absorption and then into emission. Now this isn't in the Big Bang, it's well after the Big Bang, but it's still a redshift of about 10 or 15. And that means that instead of being at 1.4 gigahertz, the 21 centimeter line is down at about 30 to 50 megahertz. Now, that's pretty much impossible from the ground. People are trying to do that from the ground, but I think it's impossible. So this was a mission to go into a lunar orbit that's very low above the moon. Since the moon has no atmosphere, you can just about skim over the mountains. And that means it would be shielded from the Earth for half the time, because the moon would be in the way. Clever idea. I mean, it's $500 million. So this is not cheap, and then less a launch. But on the other hand, people kind of want to go back to the moon, and it'd be an interesting thing to do with the moon. So we're studying that mission. If we could have a low-frequency radio telescope in space, there's all kinds of interesting things, both cosmological, extragalactic, and this galactic stuff. But it's expensive. I think I better wrap this up. I've been chatting for a while. Let me skip over some of it and finally show you my conclusion. There's a lot of statistical analysis that I've been doing, and I don't have to bend your ear with all of that.
You've got plenty of time, John.
Well, thanks, but really, here's my conclusion slide. From floundering around with this stuff for a couple of years now, my conclusion is that there is a rotation measure horizon, and that at the wavelengths of the Park survey, at 250 to 500 megahertz frequency, that horizon is a few hundred parsecs away at intermediate to high latitudes. At the high frequencies of the DRAO survey, the rotation measure horizon is at least a kiloparsec, 1,000 parsecs away at intermediate latitudes. Low latitudes are immense, and I think that with these telescopes, we don't have enough resolution to study the polarization. That is, there's too much structure unresolved by the beam. Pulsars might give a better calibration of distance. What I skipped over was comparison between pulsars, where we know the distances, and the emission in the polarized emission, where we don't know the distance. But my conclusion is, it helps a lot to do that, but we need more pulsar distances and more pulsars. But someday we will know the rotation measure versus distance function all over the sky, just as we now for the Milky Way know velocity versus distance, and we call that the rotation curve of the Milky Way galaxy. That allows us to translate spectral features to get what's called kinematic distances, which tells us how far away the things are. If we could do something like that with polarization, that would be opening a new window. Well, we're kind of opening a new window as it is. There's my little crab part, or I guess the fan region on the left. Already, all of this is opening a new window. We just don't know what we're seeing through that window yet. Thank you very much.
John, are there any more questions?
I just wonder, is it too early to ask this question, or is it not within the parameters and the scope of what you're looking at? Is it a question for another day for other scientists?
I'll answer it.
Once you've evaluated all this,
Yep.
what is it going to teach you or help you with, open up, or is that something that perhaps once we understand it, we can figure out what it will do for us? And as a secondary question, something I hung on very early in something you said. You talked about if it wasn't polarised, they would not be captured within the galaxies. So what purpose are they serving? If they weren't polarising, they'd all be going out. What would not be happening?
Well, that's a good question. They're both good questions. Let me answer the first one first. And there's always some of what you said that is, we'll understand what it's good for once we figured it out. There's always some of that. But in science, it's good to have big dreams. For example, the geneticists had this dream of sequencing the whole human genome back in the 1980s. And they didn't know how long it would take. They thought it might take 100 years. But because that was their project, people around the world got busier and busier doing it, and in the end it only took about 15 years. So the big dream here is to be able to make a three-dimensional image of the galaxy, a picture or a model of the galaxy, with a magnetic field all kind of mapped out as if it were a tangle of ropes or something. And you know, there was this guy named Gilbert. There's a magnetic field unit called the Gilbert, although it's not an SI unit. Back in the 1600s, he spent much of his life trying to convince the King of England that the Earth has a dipole magnetic field. And the reason he tried to convince the people in England, it wasn't just the king, it was the astronomers too, was that he thought he knew why compasses point north and south. Well, everybody knew compasses pointed north and south, but they also knew that it didn't always work. And particularly when they sailed up north into the North Sea, the compasses deviated from north. And Gilbert said, well, it's because the magnetic field is a dipole. And he was the first person, he didn't use that word, but to picture what a dipole field would look like. But it's not aligned with the Earth's axis of rotation. Now, it turned out to be all exactly true, but nobody had a clue what it would be good for, except for, you know, compasses for ships. But even that was important enough to them that they did map it out. And you know, astronomy, studying the Milky Way, studying other galaxies, it's not a payoff type thing. You know, we don't get corporations. SpaceX helps us out. You know, we can use our tools to do things on the Earth and in near Earth space, which are helpful. But what drives us with the tools is those big dreams, and that's what this is. So that was your first question. Now, remind me your second.
The polarization keeps it within the galaxies.
Yeah.
What would its purpose is it serving? If it wasn't there, what would be happening or not be happening? And conversely, if it didn't polarize, they just shot out.
Well, I've thought about that some, and I've talked to other people who've thought about it. There may be galaxies that the magnetic field just kind of points out, and the cosmic rays just scream out. And the reason I say that is that there are galaxies where we see these long jets, which are also cosmic rays, but they go way out of the galaxies. Sometimes a megaparsec, you know, a million parsecs, way, 10 times further than the galaxy. So it doesn't have to be like it is in the Milky Way. And one of the people in this team who studied this claims, and I think he's right, that around the galactic center there are jets where the cosmic rays are not confined to the galaxy, and even in our Milky Way, that they shoot out above and below the plane. And he traced that with polarization. He did it in a different survey, but with the same kind of polarization. Whether it does our galaxy much good to trap the cosmic rays as it does is a deep question. And you know, cosmic ray physicists would say it does us a lot of good because we can study the cosmic rays and figure out where they came from and how long they've been trapped. Whether it would change the evolution of our galaxy, the history of our galaxy, star formation in our galaxy, if we didn't trap them, that's a pretty profound question. And I guess I would say it's not obvious. It's not obvious.
Yes, the fact that it's not just all galaxies, they're variants, then yeah, that kind of.
You know, ellipticals and spirals are so different.
Yeah.
And this is something where it's not just ellipticals and spirals. Some spirals also have jets that come out, but the ellipticals do.
So comparing universes, comparing different ones that do and ones that don't, is that part of what you're looking at in your research?
Yeah, I mean, it's part of the question. We pretty much know that the Milky Way doesn't leak cosmic rays too much. And curiously, the way we know that is that some of the cosmic rays are actually radioactive elements. And by dating them, by looking at the abundance of the radioactive elements, we can tell pretty much that the whole kind of gas of cosmic rays sticks in the galaxy for at least 1 million years. They leak out, but only on longer timescales than that. So that means they travel for 1 million light years since they're going at the speed of light. And yet the galaxy is only about 20,000 light years across, or 50,000 light years across. So they go around a lot. They wander through the galaxy for a long time. Yeah.
Why do spiral galaxies have arms?
Oh, that's a good question. Yeah. And the deeper question, which is similar, is why don't they wind up?
Yeah.
Because if you look at a spiral galaxy, and people have done these beautiful computer simulations, the inner part goes around about 10 times in the time it takes the outer part to go around even once.
But then it would be a mess, isn't it? The fact that they form, they must all be spinning at the same rate, which they shouldn't do because the distance from the
certainly galaxies, subspiral galaxies, do not have solid body rotation curves. A record has a solid, my arms have a solid body rotation curve, but that means that they have to go faster the further out you go. And they don't. Most spiral galaxies have flat rotation curves. And that so-called spiral arms winding problem goes back to Lindblad in about 1920, 1930. Because he realized that there was a problem there. Because half the galaxies in the universe are spiral galaxies. They had already by the 20s, they had beautiful photographs of spiral galaxies. And it wasn't real. Now, you can argue that this hasn't really been solved, but there is a theory that goes back to about 1968 called the Lin-Shu theory, which is that spiral arms aren't material arms, they are waves. And the arms propagate as waves with a constant pitch angle, meaning that the shape, whether it be like a pinwheel like in an SC or a more wound up thing like in an SA, that shape never changes. And the whole thing propagates along kind of like a wave in the ocean. It moves through the galaxy as the galaxy rotates, but it itself doesn't wind up. And I teach that theory. It's a very elegant and beautiful mathematical theory, but it probably doesn't apply to all galaxies. Well, so the way, one of the ways you can sort of tell that that does apply is that a lot of galaxies have a bar in the middle, and at the end of the bar is where the spiral arms start, and then they wind out from there. And that's kind of a prediction of this theory too, that there should be an inner edge to the spiral pattern called the inner nebula resonance. So I think we sort of know the answer to that question. A tough question and puzzled people for a long time. Okay.
Other questions? We're getting some good questions. No, we're getting close. Last opportunity. Well, John, I realise you faced a challenge this evening because you're deeply in your research, and it's very technical research. It's fancy research.
Thank you all for your patience.
Tonight you have managed to distill some of that out for us, and distill some ideas out for us that I think all of us have understood enough about, certainly to ask some good questions. So I think the fact that there have been some really searching questions here tonight are a testament to you that you've taken the very technical to a level that we can touch and understand. But I was beginning to think that, then you put your big main formula up, I thought, oh, I wonder how far John's going to go with that formula. There might not be many people here that could solve the formula. But no, you stepped on, which is good. So we had that range of questions. I was interested to hear you comment about, or someone asked a question about citizen science as virtually here, and you made a comment, well, there's another project that could potentially be a citizen science project, or some input to that. Could I just take a leave for the moment and just ask, would that be of interest to hear about?
Great, absolutely. Well, let me say, I want to give that to my group at the university first.
Oh, yeah.
See if I'm totally not saying because it's a pretty wacky thing.
Well, there's a receptive group here if there's an opportunity.
Thank you.
So that's good. So I think without further ado, I'd like all of you to sort of show by acclamation and thank you for Mike, do you wish to just run up the meeting now?
Yeah, no, that's about it, I think. Yes, thank you again.
Yeah, sure.
That's been terrific. So we're a bit ahead of time, but I think within the next few days we'll send out a newsletter just to confirm those dates on the working bee and a few more volunteers on the night of the 21st. So thank you for your attendance tonight, and till next time.
So,
Yeah, thank you.